Hey everyone, this is lecture number 2 from the class. Lecture number 1, we covered statistics. We talked about fundamental concepts of statistics, sampling, and so forth. Now we're going to talk about probability. In this, I will break up this lecture into 2 separate parts. The first part will be fundamental concepts of probability definition, Venn diagrams, and get into frequentist concepts. I'll split out Bayesian concepts and record that as a separate video. I would acknowledge that for this course material I benefited from taking some of the concepts and some of the ideas directly from Dr. Larry Lake and Dr. Zoya Hadari's previous 337 courses. I want to acknowledge them. So let's get into it. We'll get started with some basic definitions and rules. So probability. Why do we care about probabilities? How does this help us in what we're doing as engineers? And it turns out that probabilities are essential given the fact that we have uncertainty to helping us make decisions. And I'll give you some examples right here. What is the probability that a well is successful? Well, from that directly, you can make the best decision about whether or not to drill the well. What's the probability that a valve is cracked on a blowout preventer or something like that? And you can then make the decision of whether or not you should replace the valve or take some other remedial action. What's the probability that the seismic survey finds a reservoir? You can use that to justify directly whether or not you should spend the potentially tens to or more millions of dollars in order to acquire that seismic survey. What's the probability that a reservoir seal will fail? That'll help you determine whether or not it's safe to sequester carbon dioxide in that reservoir for the foreseeable future. I can remember in Australia when we were looking at carbon sequestration, we were concerned about whether or not the seal would hold up for 1,000 years. And so you can imagine those are very hard things to work out, but if you can assess those probabilities, they help us make very important decisions within our business. So most of our decisions involve uncertainty, and so we need to quantify probabilities in order to inform those decisions, to make the very best decisions possible. So let's talk about exactly what a probability is. And so a probability is a measure of a likelihood that an event will occur. For random experiments in well-defined settings such as coin tosses, this is quite straightforward. And so the frequentist approach is that the probability is the limit of a relative frequency over a large number of trials. And so we can denote this as the probability of event A, and A can be anything that we define. And we can shorthand that as P of A is equal to the limit as N, or the number of trials, goes to a very large number, of the number of trials that A occurred divided by the number of trials for all possible occurrences. Omega represents all possible things that can happen. And so this, in fact, is just a ratio. We can look at if we have a hat and we draw red and green balls, and if we draw 5 red balls out of 10 draws, we would say 50% chance of getting a red ball. That's exactly what this is telling us. Of course, this is suggesting that we have a large enough set of trials that we can in fact assess these statistics. And so an example of drilling a dry hole for the next well, or encountering a sandstone at a location, remember our location vector U, and alpha is just indicating one specific location, exceeding a rock porosity at that location, and so forth, would all be possible event A's that we could assess through looking at multiple occurrences. And so that's the frequentist approach. I like to think of frequentist approach as just being I count to get to probability. I just count and take ratios. And so if we're trying to represent probability, Venn diagrams are very powerful. They provide us a tool to communicate and to visualize probability. And so we can look at in an experiment and multiple possible outcomes or samplings from that experiment, and we can look at multiple different types of events that may occur. And so we have omega, which represents all possible outcomes, and we draw a box. You must draw the box. The box indicates all possible outcomes. We label it as omega. Then within those all possible outcomes, we can draw a circle or shape that represents all the times that A occurred, A being some specific outcome. As mentioned on the previous slide, it could be a specific porosity threshold is exceeded, a crack formed in a pipe or something. B would be another possible event. And so we could draw a circle or some shape around the area of all possible outcomes that's represented by B outcomes. And so what do we learn from a Venn diagram? We've represented the probability of these two different events within all possible things that could happen. Well, first of all, the size of the regions directly is proportional to the probability of occurrence. You notice here that B is maybe roughly about 2 times the area, about give or take. So we could say that B is going to be about 2 times as likely. In fact, we could suggest that the probability of B would be the area of B divided by the area of A as likely as A. Then we have overlap. What if the shapes are overlapping with each other? This would be the probability of joint occurrence. Right now, these shapes do not overlap with each other, and so we could suggest that there's no probability of both A and B occurring at the same time. So this is an excellent tool to be able to visualize marginal, joint, and conditional probabilities. We'll talk about that as we go along and get more into conditional and joint probabilities. Okay. So let's give ourselves a very simple example of a Venn diagram. So we have an experiment. We did some type of sampling. The sampling had 3,000 cores that were measured along 1-foot increments. And so, we have a set of well cores, and we've measured 3,000 measurements along 1-foot increments along this long length of core. And so the sample space, omega, is going to be the facies, sandstone or shale, along the entire length, along those measures of 3,000. And then we have defined our events A and B. In this case, these events are going to be facies. And the facies can be sandstone, it can be shale, or some other types of facies. They're discrete categories. And so we're concerned about whether we have shale or sandstone in this example right here. And so what we can see here is that, first of all, relative shape or size, we can see that we're much more likely to have shale than sandstone. We can also see that it's possible to have both shale and sandstone at the same time. Therefore, there is some type of a mixture of the two, sandstone and shale. Maybe it's an interbedded sand-shale type of rock. And then finally, you'll notice that the circle, or the areas for shale, sandstone, and both, do not cover the entire omega area, all possible outcomes. And so that tells us immediately that there must be some other facies beyond shale and sandstone in the interbedded that we are not talking about with our specified events. There are other things that can happen too. Now, let's talk about some of the operators related to probability, and we'll visualize them with Venn diagrams, which is quite useful. And so first of all, we have a union event. All outcomes of sample space that belong to either event A or event B. So the union, represented by this U symbol here, is like an OR. Our events exist within A or within B. And so in order to calculate unions, all we have to do is take and combine the areas of each one of these events together, and the result is A union of B is going to be all of this put together. The intersection is the idea of outcomes in the sample space that belong to both A and B at the same time. It's represented by this upside down U symbol over here. That's an intersection, and it's represented by the set for which X belongs to A and it also belongs to B at the same time. And so schematically, we represent it with this purple area right here. It's the intersection of the region A and B. We can also have complementary events if we're talking about operators. This is all outcomes in the sample space that do not belong to a specific event. And so if we take a look at our omega, which is all possible events, We have A, which are all events of type A. A complement will be all events that do not belong to A, in other words, this white space. Mutually exclusive events. These are events that do not intersection and do not have any common outcomes. And so this is a good illustration like the one we saw before, where we have events A and events B, and they do not overlap with each other. There are no cases of intersection between the two. We denote this as A intersection with B is equal to null set, indicated here. In other words, there are no samples which have belong to both A and B at the same time. Then we have the case of exhaustive, mutually exclusive sequence of events. And so these are sequence of events whose union is equal to the sample space. And so let's take a very simple example. And so we have our omega space, which is shown right here. And we have event A and event B. Notice that there are no white spaces. This suggests that we have, in fact, events, a set of events, which are exhaustive. They cover all possibility. There's nothing that falls outside of them. Then notice that A and B do not overlap. They just touch perfectly along this line right here. That suggests that they are mutually exclusive sequence of events. They don't have overlap. You're either A or B. You're never both at the same time. And so in that case, if we take the union of the first event, the next event, through all of the events, that will be equal to the entire omega sample space. That is exhaustive, mutually exclusive sequence of events. So now we can refine our concept of probability. We can talk a little bit more specifically about it. And so we can talk about the fact that according to our Venn diagram, the probability of A occurring is really a representation of the ratio of that area of A divided by the total area of the sample space. And so we can recognize that if we're talking in probabilities, the probability of belonging to omega is going to be 1. We have a 100% chance that our event is going to be within omega. And so we could talk about different examples of this. We could talk about the possibility of drilling a dry hole in the next well, which would be a complement. If we were to suggest that event A would be drilling a hole that's not dry, and encountering sandstone at a location, which could be represented by B, exceeding rock porosity of 15% at location U alpha, which could be event C. And so now we have a joint intersection of events, A complement intersecting with B, intersecting with C, and we would be talking about the area of A complement intersecting with B, intersecting with C. So we can take that area that's intersecting with B and C, and we can subtract from it the area that is actually within A, and we get that area right there. And so we can solve all kinds of complicated problems and look at all specific types of combinations of events as shown right here. We will later introduce the idea of joint probabilities. But we can do that by using these Venn diagrams in this approach. Now, it's a very nice way to work this out as we're talking about intersections and unions is to go to a specific example. And we'll give ourselves a very small data set. And in that data set, we'll say that, okay, the petrophysicist has measured porosity on 7 core samples from a carbonate formation in the laboratory as follows. So this set, 1, 2, 3, 4, 5, 6, 7, are 7 samples that have been conveniently ordered in increasing order. And so we have our multiple samples shown here. And now we can define our events. And so to keep this very simple, we just define our events with basic thresholds. We say event A will be porosity values less than 15%. Event B will be porosity values greater than 20%. And event C will be porosity values between 14 and 17, between and including 14 to 17%. And so if we do that, we'll find that our data set, our event A will include the samples 10, 12, and 14. Event B will include only the sample 0.25 or 25%, and event C will include the values 14, 15, and 17. And so for convenience, I've drawn these color bars to indicate event A, event C, and event B. And so now we can start doing some really basic type of calculations using our union, our intersection, and our complement concepts in order to look at the specific sets of values that meet these criteria. What I'll do right now is I'll invite you to pause the screen and go ahead and fill these out, find these specific events that match these union, intersection, and complement criteria, and then go ahead and press play to see the solution. And so I hope this is what you got. I'll just look through a couple of them with you. If we take A union with B, now we're getting all of the lower values, plus we get the value within B that was higher than 20%, and we combine them together and we get this set right here. If we try to take the intersection between B and C, if we go back, we'll see that B and C never intersect with each other, and so the intersection of B and C results in a null set, and so forth. So you can work through all of them and see the results. If you take the union of A, B, and C, you'll notice that the only value that's missing is the 19% because it belongs to none of the events, so it would not be in the union. And so the next thing we could ask ourselves is, what's the probability of each one of these possible sets of unions, intersections, and complements to occur? And so that's pretty straightforward, because all you have to do is take all of the events, the number of events that belong to those sets, and divide by the omega, the n omega, which is just the total number of samples that are available. And that is 1, 2, 3, 4, 5, 6, 7. And so this will be 4 divided by 7, the probability of A union with B. The probability of B intersection with C was just a single event, so it's 1 divided by 7. The intersection of B and C once again was 0, a null set. And so the probability of that occurring is going to be equal to 0 divided by 7, which is equal to 0, and so forth. And so you can go through and you can see all of the possible events. I apologize right here. I just noticed that there's a mistake. 19 has been added in. It should be removed. It should be 6 divided by 7 for a probability. I'll get that corrected. So let's talk about non-negativity and normalization. So there are other fundamental probability constraints that we should look at. And these really get at kind of just very axiomatic type of ideas. The first one is that a probability is bounded. It must be greater than or equal to 0, less than or equal to 1. In other words, you cannot have a negative probability. You cannot have a probability greater than 1. That would not make sense. The other thing is that all possible outcomes, the probability of every possible outcome is equal to 1. And that makes sense. That if we look at all possible things that could happen, if we're going to consider all of them being within our set, then of course, what we get back will be something within that set. It was all possible were included. We could also consider the null sets, and that is the probability of a null set. In other words, there's no samples within that set, is equal to 0. In other words, if there's no outcomes like that, the event is empty, then it has a 0 probability. Closure is interesting too. Closure is quite straightforward, and it suggests that the probability of A complement, all of this white area, of A not happening, plus probability of A happening, is equal to 100%. That's closure. Okay? Let's talk about the addition rule, and we're getting into a little bit more complicated operators, but it should still be pretty straightforward. So let's take the problem of calculating the probability of the union of A and B events. And so we have A, we have B, and we have drawn on purpose some intersection of A and B. It is not a null set. There are occurrences or events that have both A and B. And so we can use the addition rule. We can say that the union, the probability of the union of A and B, is equal to the probability of A plus the probability of B. But if you're really careful, if you look at it, what you realize, if I take the probability of A, all of it, and the probability of B, all of it, I'm double accounting for the intersected area. And so what we do is we subtract the intersected area between the two. And if you do that, you get the probability of the union of two of these. Now, if you have mutually exclusive events, like we've drawn down here, you don't have any intersection area. And so you can calculate the probability of the union of all of those events simply by taking the sum of all the probabilities. The probability of A1 plus the probability of A2 plus the probability of A3 plus the probability of A4 would be equal to the probability of the union of A1, A2, A3, and A4. There is no intersections to count for, so it's quite straightforward if they're mutually exclusive from each other. So here we go ahead and we'll do a very simple example, and we're going to calculate the specific probability shown here. We have the probability of A, probability of B, probability of A intersection with B, probability of A union with B for each one of these cases. Now, I didn't want you to have to calculate the areas, so what I did is I defined the spaces for each one of them. It's no longer a Venn diagram. In fact, what I've done is I've just defined the cases within porosity permeability, which I call B, which I call A. And now we're going to just solve for this using the simple approaches that we described on the previous slides. Hint, this literally is an exercise in counting points inside of circles. It's not that bad. And so go ahead and try it for this one too. I'd ask you to right now pause the screen, and then I'll go forward and I'll show you the answer. So this wasn't so bad. As I said, it was just point counting. So the probability of A is just going to be equal to all of the points that fall within the criteria of A divided by the total number of points. 6 points here divided by 20. That's all. Probability of B, just as easy. Probability of A intersection with B is just going to be 0 because there's no cases for which the criteria of A and B overlap relative to porosity and permeability. And the probability of the union of A and B, well, we already calculated the probability of A and B, so we're good. We just put those down. The intersection between the two is equal to 0%. Oh boy, I just noticed that. Sorry about that. Here, I just made a correction in my notes. I apologize. That should be 0% right there. I should have seen that. All right, so let's move on. Now, if we go to this example here, it's a little bit more complicated. We have 8 events that exist within A, 6 events that exist within B, so we can calculate those probabilities pretty straightforward. The intersection between the two is simply going to be these 2 points right here, 2 out of 20, 10% chance of that. The probability of the union between them, we can now calculate it quite straightforwardly. We got probability of A 40%, probability of B 30%, probability of A and B is 10%. We subtract it off, and we'll find that the union of A and B has a 60% probability. Now you might wonder if that's correct. The thing about doing this point counting approach, let's check our work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 20, that's 60%. We correctly accounted for the fact that we're double counting those points there. We're good. Now let's get into conditional probability. This is a very interesting and powerful concept. And so when we talk about conditional probability, we're talking about the probability of B occurring given A already occurred. We denote it like this: P, B. Every time you see this vertical line, read it as given A. You could also write prob or probability, but we just put P for shorthand. Now, how do we calculate that probability of B given A has already occurred? Well, we do it right here with this equation, which is the conditional probability equation. Probability of B given A is equal to the probability of A intersection with B divided by the probability of A. Now let's look at our Venn diagram and we can understand this. We got the probability of A, or A event. We got B event. We got the intersection between the two. I want the probability of B given A occurred. Well, A occurred. Omega is no longer relevant. We know that A occurred, so we shrink our universe down to A. So now I take that square away, and this is our universe right here. Everything that we know now is A has occurred, and so we're here. So how do we calculate the probability of B given A has occurred? We take the intersected area, probability of A and B, intersected, I mean, with B, and we divide it by the probability of A, which is our new universe. So it's interesting, we shrunk down the universe is one way to think about it. Another way to think about it is we're taking the intersected area and we're standardizing or normalizing by the area or the size of that universe. So that's conditional probability. Now that we've learned about conditional probability, we can put some labels on things and we can complete some knowledge about the concepts of conditional, marginal, and joint probability. Okay, so conditional probability is shown just like this. It's the probability of B given A is one example. The probability of A and B is known as a joint probability. It's a probability involving two separate occurrent events at the same time. It could be two separate variables, whatever it might be, but it's two separate considerations at the same time. A marginal probability only considers one thing at a time. It's not thinking about multiple events or anything, it's just thinking about one thing. And so that's the marginal. So we got a conditional is equal to the joint divided by the marginal. So now we've introduced these three concepts. Let's go ahead and look at a very simple relationship. We got a permeability distribution shaped like this, with permeability values going between some amount of millidarcies to some larger amount up here. And we got porosity, maybe going between like maybe a couple of percent to maybe 20% or so here, a distribution of porosity. And then we have the relationship between permeability and porosity scatter plotted and then shown as some type of probability contours right here. This is a bivariate distribution, a distribution between two variables. This is univariate distribution, a univariate distribution here. Now let's talk about marginals, joints, and conditionals. The marginal would be if I took porosity and said I'm concerned about porosities between, say, 20 to 24% or some number right there. What's the probability? That would be a marginal probability. Now, if I went to permeability and said I'm concerned about 100 to 200 millidarcies right here, and what's that probability? Right here, that would be a marginal probability for permeability. Now, if I took those two constraints, 100 to 200 millidarcies, and going from, I think I said 20 and 24 or something, porosity units or percentage down here, I would get a square. Permeability constraints, porosity constraints, and if I calculated the probability of having both, samples having both that range of porosity and that range of permeability, that would be a joint probability. Now, if I was to go here and say porosity between maybe 10 to 12%, what is the distribution of the, I could look at the specific distribution of permeability, that would be a conditional distribution. And so if I started talking about, well, what's the probability of a certain permeability value given that range of porosity values, that would be a conditional probability. So the power here is conditionals, marginals, and joint probabilities allow us to explore and understand probabilities of single things occurring or multiple things occurring at the same time. Now, we use shorthand all the time, and we want to make sure nobody gets confused by that. A marginal probability, the probability of an event without any consideration for any other event, could be denoted like this. Example, probability of event X, Y, or so forth. Conditional probability, the probability of an event given another event has already occurred or is true, is the probability of X given Y, probability of Y given X, and so forth, but we also shorthand it with the bar, with the vertical line to say given. We read that as given once again. A joint probability can be represented as a probability of event X and Y. It can also be represented as the intersection, which we've already been talking about. The intersection operator is a joint probability, or we can just put a comma. And so these are three different ways to denote the joint probability. Probability of X event and Y event occurring at the same time. So what's the general form for conditional probability? we can now jump a little bit further down. We can get a little bit more complicated here. And so we can say that the probability of C, event C, given B and A is equal to the probability of A intersection with B intersection with C divided by the probability of A intersection with B. And so this is really powerful, right? We're getting to the point where we're saying, okay, what if I shrink my universe to A and B both occurring? Now what's the probability of C occurring? So you can see that's this area divided by this area right here. And so graphically we can see it in the Venn diagram quite well. Now let's take that equation, which we can demonstrate with the Venn diagram, and let's recall that the conditional probability form for two events that was shown right here. We can use that, manipulate it, put the probability of A on this side, pull it out and put it on this side, and we can substitute this for that, and we get this form right here. Then we can take that and pull it out and put it on this side. If we reorganize it like that, we get the probability of A intersection with B intersection with C is equal to the probability of A times the probability of B given A times the probability of C given B and A. And so this is a very general form. It's the recursion form of conditionals, and we can expand it like this, and we can go on forever. Why is this powerful? It turns out these joint probabilities are very hard to calculate in practice, and when we get into stochastic simulation, that's a perfect example where we're just unable to calculate the joint. And so what we can do is this is a marginal, this will be a conditional, 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 conditional that all build on each other. And so it's much easier to calculate going from marginal to a set of conditionals. We can get at a joint that we would not have been able to get at usually. All right. So let's talk about just one more thing about conditionals, and then that's order relations with conditionals. And so you recall the order relations with the regular marginals suggested that the probability of A plus the probability of A complement is equal to 1. But what else is true is that we have closure when it comes to conditional probabilities. The probability of A given B plus the probability of A complement given B is equal to 1. And the probability of B given A plus the probability of B complement given A is equal to 1. And so this is pretty easy to visualize. If you go ahead and take one of these examples, we shrunk the universe, A occurred, probability of B given A. And so A has already occurred. The universe is this now. And so the probability of B given A is this part right here. Probability of not B given A is this part right here. And we've already shrunk our universe, so now all possible outcomes in the conditional realm are all described within A. So that is equal to 1. That's closure now. So that's a very powerful concept. We'll use it when we get into some of the Bayesian statistics. It's going to help us out using this closure with conditional probabilities. So we have another example to work through right here. I'm going to ask you to go ahead and pause the video, and go ahead and work this out. This should be a little bit tricky. It should be a bit tricky. It'll get you kind of thinking. You don't need to calculate. You don't need to calculate any areas. You should be able to do it just by using probability A's and B's. All right, let's go through the answer right now. And so the probability of A given B, we can use the general equation of the conditionals. And what you'll find for both of these is that the intersection between A and B is equal to 0. And so both of them will have a 0 probability. For the second case, this is very interesting. If we take a look at the equation, probability of A given B, we get the probability of A and B intersection over the probability of B. Now what's very interesting is that the probability of A intersection with B is equal to the probability of B, because B is completely contained within A. And so if you substitute that back in, you'll see that's equal to 1. It's equal to 100%. The probability of A given B, they're all A, so it's 100%. Probability of B given A is also very interesting because in this case, once again, the intersection of A and B is equal to the probability of B. If you substitute into the equation, you get the ratio of the probability of B divided by the probability of A. And that makes sense. You shrunk your universe to A. And so it's just the size of B relative to the size of A for the conditional probability. Okay, so I'll give you another example right here. This is going to be more point counting again, so this will be pretty straightforward, but it gets at a fundamental idea, and that is, how much does porosity tell you about permeability, and how much does permeability tell you about porosity? So go ahead and calculate the conditional probabilities of A and B, where event A is porosity greater than 15%, these points right here. Event B is permeability greater than 200 millidarcies, all these points up here. Calculate this and then give some thought to how much information does B tell you about event A and vice versa. Are they meaningful? I'll give you some, well, you'll have as much time to work on this. You can hit pause and start again. All right, here's the answer. Okay, so I drew my events A, B, A here. And so it's pretty straightforward. It's point counting, right? The probability of A intersection with B is going to be these 8 points right here divided by 20. Probability of B is going to be all of these 11 points right here. I added these 3 in. And so it's pretty simple to solve. It's 8 divided by 11. We try to avoid using calculators in this class, right? And so we can go ahead and look at the probability of B given A, which is pretty straightforward too. Now the question is, how much information does B tell you about A and vice versa? How would you show that? And so this is interesting. If you could calculate the probability of A, the probability of A given B, and then you just compare them. This is the probability of A given you knew nothing about B. This is the probability of A given that B event was known. That's information you have about B. And if they're different from each other, it tells you that there's shared information. It tells you that B tells you something about A. And so the probability from just A alone was 50%. As soon as you added in given B, the probability of A occurring jumped up to 73%. It's telling us that they share information. You can't work with A and B independently. They provide information about each other. And here's the opposite case here. And so that would be one way to show kind of how much does B tell you about A and A tell you about B. Okay, so we learned about joints, marginal, and conditional probabilities. Let's go ahead and look at this example right here. And we're going to work this out by hand. And once this is done, I promise you, you should probably know the idea of a joint, a marginal, and a conditional quite well. You should have that now. Okay, so let's look at the distribution of these joint probabilities. And for simplicity, we just used cells. So we broke up the problem. We got fraction of shale here. We got porosity. This came from a bunch of different samples that were available to us. And so we go ahead and within each one of these cells, we have the joint events, the frequencies, the joint frequencies. I've just plotted them here. And then so we've done that. We have all of these frequencies. How would we go to joint probability? Well, it wouldn't be very hard. We know that if there was 25 events, I should say, or samples, that every one of those samples is worth 4%. And so if you just toggle back and forth, you see that's how I did. This cell had 1 sample, 4% chance. This one had 3, 12% chance, and so forth. So now we have all of the joint probabilities. And so the question becomes, how do you go from joint probabilities to marginals? And how do you go from the joint probabilities to a conditional? What's the conditional probability of V shell 10% given you have a porosity of 15%? This is your universe now. Okay? So I'll give you, well, take as much time as you like. Pause me. Go ahead and work this out, and I'll give you the answers right now. All right, so here's the answers for us. And so, first of all, the marginals are pretty straightforward. What you have here is if I want to calculate a marginal V shale or fraction of shale, 10%, 30%, 50%, and so forth, remember, I'm not concerned about porosity whatsoever. I don't care about the porosity values. The marginal only considers one event at a time. So all I have to do is sum all of these joint probabilities. I'm integrating over them, and that's the result. So I've got 4 plus 4 plus 8, 16%, and so forth. So I'm just summing down to get this marginal. To get the porosity marginal, I'm just summing across to get that marginal right there, and these are the values. The conditional distribution is interesting. We shrink the universe to be only the cases for which porosity is about 15%, give or take. And so we've got how many cases like that? We've got 2, 1, 2, 2, 1. 6 cases like that. 1, 2, 2, 1. Okay. So what we can do is we can calculate the conditional as simply being this joint right here divided by the marginal. And so that's 1 case divided by 6 possible cases within that marginal. And so then we got 2 out of 6, which is 1/3, 1/3, and 1/6 again. And if you look, we have closure for the conditional because all of the cases within the conditional, this sums to be 100% right here. So that's how we're calculating marginals and conditionals directly from joint probabilities. Okay, let's talk about the multiplication rule. So we had already shown that the conditional probability B given A is equal to the joint of A intersection with B, A and B, divided by probability of A. So we can manipulate the equation and we get this multiplication rule. The joint A and B is equal to the conditional times the marginal. And so what do we know? Well, we know if events A and B are independent from each other, that this conditional, the probability B given A, is just going to be simply equal to the probability of B. A doesn't tell you anything about B, so this is going to be equal to the probability of B without considering A whatsoever. So that's a condition for independence. Knowing something about A is not going to help you do anything to predict B. And so then by substitution, we get this. The joint probability of A intersection of B, or the joint of A and B, is equal to the probability of B times the probability of A. And the general form for given independence for all possible events is just simply the intersection or the joint of all the events is going to be equal to the product sum of all of the probabilities. This is pretty straightforward. And so how do we use this in practice? If we have independence between our events, we can solve our problems using the multiplication rule. And so if there's independence between fluid type and porosity, we could have a problem where event A is oil, fluid type is oil, event B is porosity good, greater than 10%, and we could say the probability of oil is 30%, the probability of good porosity is 50%. What's the probability of both of them together? And we have another case where we added saturation greater than 40%, and we could look at the possible probability of having all three of those events at the same time. Go ahead and just do that. That should be pretty straightforward. Pause it, and I'll give you the solution right now. Okay, so multiplication rule. The probability of the joint A and B is equal to the probability of A times probability of B. And so we find that 15% chance or probability of having good porosity and also having oil. And we can go ahead and extend that and add the probability of having a certain specific amount of oil saturation. And we can see that now we have a 1.5% chance of those three things occurring together. That's independence. Now, events A and B are independent if and only if the probability joint, the A intersection with B, is equal to the probability of B times the probability of A. So we can check for independence, or at least try to disprove independence, by looking at the joint and the marginals. If that holds, then we have not disproved independence. They may be in fact independent. If that doesn't hold, then immediately we can say that they're not independent. The probability of A given B is also should be equal to the probability of A, and vice versa. Probability of B given A is equal to the probability of B. And so that is those are required in the case of independence. And so the general form is, as we discussed before, the general concept of the expansion of the multiplication rule for any number of events must be equal to joint of all those events together must be equal to the product of all of their marginal probabilities. And so this allows us to solve some really interesting problems. Let's go ahead and look at this problem right here. We've got 9 wells. In each one of the wells we have 3 different categories: facies 1, 2, and 3. 10 wells, sorry, there's 10 separate wells. And so we'll define event 1 or A1 as being F1 in the middle faces. All of the times that you have F1 in the middle faces is event A1. Event A2 is F3 in the bottom faces. So this is interesting. So we could use these relations right here to test for independence. Are A1 and A2 in fact independent of each other? So let's go ahead, solve for that, and I'll give you the solution in 3, 2, 1 now. Okay, so the easiest way to do this is just draw circles. Remember, we're frequentist statisticians now. Everything we do is by counting until we get into that Bayesian stuff, and even then we'll do a lot of counting. So let's draw circles. A1 is middle faces F1. 1, 2, 3, 4, 5 out of 10. So we've just done that. We just solved for, in fact, the probability of A1 is 5 divided by 10, 50%. A2 are all the cases of F3 in the bottom section of the reservoir. 1, 2, 3, 4, 5, 6. A2 probability is 60%. The intersection of A1 and A2 are these square boxes right here. That's 2 out of 10, that's 20%. So we can put that into an equation, and we have the probability of A1 times the probability of A2, 50 times 60%, is equal to 30%. Is not equal to the joint probability of A1 intersection with A2 of 20%. What's that tell us? That it's non-independent. So this is important because now if we're trying to make predictions about reservoir, we might be missing some data in another well. And we might know about the middle, but not know about what's going on in the bottom unit of the reservoir. If we know they're not independent, we could use information from the middle of the reservoir to predict at the bottom of the reservoir, and it would provide us with some information. If they were independent, or we could suspect they're independent, we could use different types of tools for calculating probability, which are much easier to work with, and so independence makes our life easier if that is the case. So when we're thinking about different conditional probabilities and marginals and so forth, we can start in the multiplication rule. We can start thinking about this idea of a tree. The easiest example for a tree would be we have events A1 through A3 are 3 coin flips, A1, 2, and 3, heads and tails. And if we want to look through all possible combinations of outcomes, we could consider the first toss. You could have tails or heads. Given you had tails, you have a next toss, tails or heads, and the next toss, tails and heads. And if you take the combination, tails, 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 you get T, T, T. Heads, 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 H, 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 tails, heads, heads, tails, heads, heads. And you'll see very quickly that these are all the possible outcomes that could occur. And so what's really nice about looking through this, you can see that, well, this is a nice nice example of independence. Each one of the heads or tails had a 50% chance. You'll see very quickly that each one of these cases had a 50% to the cube power, so they each had a 12.5% chance of occurring. And we had 1, 2, 3, 4, 5, 6, 7, 8 possibilities. 8 times 12.5% is equal to 100%. Those are all the possible outcomes. And so in some classes of problems, the easiest way to solve them is to expand the problem out like this and to look at a probability tree to understand all the possible outcomes. And so you could start solving some kind of difficult problems. What's the probability of having only 1 tails? And if you do that, you'll notice that, okay, this one, this one, this one only have 1 tails. And so we start talking about the fact that that's 3 times 12.5%, 37.5%. So we'll get into the binomial distribution when we talk about distributions, and you'll see more of a mathematical, analytical approach. This is more of a frequentist type approach to work out these problems where you have a chance of success, multiple trials, how many cases with a certain number of successes or tails or heads, and so forth. But we'll leave that there for now, talking about this idea of probability trees. I should comment on the fact, that you could also start thinking about the fact that you have this first coin toss, which is a probability of heads, probability of not heads, which is tails, A and A complement. And then given you had heads, now you can talk about for the second coin toss the probability of heads there, given we had heads on the previous one. We know in that case that they're independent of each other, and so we can expand this out using the conditional. And then, of course, we could show that since they're independent, the probability of B times probability of A is what's needed. We don't need the probability conditional to A at that point, and so forth. And so all of this could be worked out for both of those cases. That's enough about probability trees for now. Okay, let's go back to the product rule and get into Bayesian statistics, but I'm going to leave the lecture right there and break it in and do a separate recording for Bayesian statistics. All right, I hope this was helpful.